everyone. How are we doing today? Doing all right? Okay, wonderful. All right. I do want to, at the start here, to remind everyone who hasn't come to speak to me prior to the final that they should do so, so I can tell you on a one-to-one basis how exactly everything works out, so that you're prepared for next week and get everything going on. But today I want to ask to see if there are any specific types of problems that you would like me to see you do examples of, or I'll just do a handful of things. Let's practice. Yes. Lagrange multipliers? Yes. Okay. We'll start with that. Okay. Well, let's see. Which of these has a better set of examples to do? Sorry. I'm picking a problem for Lagrange multipliers, but I don't know if it's better to get one out of the section or better to get one out of... We'll do this. Okay. All right. Lagrange multipliers. And what we want to do is we want to optimize this function here. Where did the problem go? There it is. And we are given this constraint here. So we have a function, x squared, y, and we have the constraint, x squared plus y squared equals 1. It means with respect to. Sometimes it's used as a phrase when you're talking about differentiating, or if there's, in a situation like this, where there's a constraint. All right, so the formula for Lagrange multipliers is this, okay? You have a system of equations that are set up where you set the gradient of the function that you're trying to optimize equal to lambda times the gradient of the constraint. And then you also use the constraint, function g equal to the constant, as your last equation. What you end up with is a number of independent variables equal to the number of independent variables in your two functions, plus a extra variable for lambda. That's why you need the last equation for the constraint. This adds a variable to it. Now, there are versions of these problems where you might have an additional constraint. Okay, I'm not going to give you one of these on the exam that has multiple constraints, but they do exist. Okay, and the way that you handle them is by working through them precisely the same way. It's just that now you have added an extra equation, and so the right-hand side of the gradient expression gets more complicated. Okay. For this problem, we work out the gradient of f and g. So the gradient of f this, taking the partial derivative with respect to x and with respect to y. And then on the other side, we have the partial derivatives of g with respect to x and y times lambda. No. I'm writing down the equations component-wise, but what I'm computing is the gradient of both of those functions. So what we're doing is we're constructing a system of equations. The gradient of f looks like this. We're setting it equal to lambda times the gradient of g. Okay, but in order for me to write it as a system of equations, I have to set things equal to component-wise. Final equation in our system is just the constraint equation. And so I need to solve this system of 3 equations and 3 unknowns. Okay. The constraint for any Lagrange multiplier problem is a function equals a constant. Okay, so this is this. All right, now we want to start working out expressions here. If I look at these first 2 equations, for the first equation, one of the things that I can do is I can ask what happens if x is equal to 0. Okay, so if x is equal to 0, it destroys both sides of the equation, and that would give us y equals 1 potentially, or y equals plus or minus 1 for the other value if I look at the third equation. The issue is that the second equation here excludes that possibility. Okay, because if I set x equal to 0, then that would mean that y has to equal to 0, and that violates the constraint. Okay, so something we need to consider, but we can eliminate through following the logic here. That means is that we can divide by x. So if we take our first equation here and divide through by x, we get this expression, so y equals lambda. We can plug that into the second equation. Sorry, I wrote lambda 3 times instead of a 2. All right, they look close enough. Anyway, yeah, 2 lambdas 2 ways. Sounds like how you would cook chicken or something. Anyway, all right, just about did it a second time. All right. Okay, so now we have 2 lambda squared here. And so that tells us that x squared is equal to this. And since we have expressions for both variables in terms of lambda, we can put those into this last equation here. Now it's very important that you keep track of how to use the parentheses here so that you don't make a mistake when you plug stuff in. Okay, x squared is equal to 2 lambda squared, and y is equal to lambda. So the grouping symbols are important here. This gives us 3 lambda squared is equal to 1. And so lambda squared is equal to 1/3, which implies that lambda is equal to plus or minus 1 over the square root of 3. Okay, I'll believe. All right. So because that's the case, we can now go into figuring out what's going on with our values. And we break this up into cases. If lambda is equal to negative 1 over the square root of 3, then y is equal to lambda, and x squared is equal to 2 times this expression. So we take the square root, get a plus or minus again. So it's going to be this, right? We square it, we get 1/3 times 2, and then the square root of 2/3 is equal to that. Again, we have another plus or minus because we have to take the square root to isolate x. We have 2 points that are given to us by this expression here, and we can evaluate those at the value for the function. Now, our original f was x squared y, so the plus or minus part in x doesn't actually matter. So if we do plus or minus the square root of 2/3 and negative 1 over the square root of 3, we're going to get this as our answer. Okay. And then we do the other side. And the arithmetic is extremely similar, except we're going to have a positive value for y this time. Okay. These 2 points are the mins, and those 2 points are the maxes. All right. As long as you were very careful about how you wrote the plus or minus signs here, I wouldn't necessarily need you to tell me that it's 2 points, because you're saying that f of plus or minus the square root of 2/3 negative 1 over 1/3 would be the 2 minimum points, and so on. Okay. All right. Make sense? Okay. Now, as you recall, the section or the problems from this section also occasionally had situations where you may have had to break things up into cases or something, assuming that 1 or 2 of the variables were 0, and maybe like have 3 different answers based on those guesses. I'm not going to give you a problem on the final that requires all of that nitpicky stuff, because we've done that type of problem already previously in the course. Number one, they usually involve 3 variables, and they also just take more time. All right, I'm putting this on the exam to remind you that this is a thing that should be in your toolbox. Okay, if you need to have a more sensitive set of calculations with those problems, you'll remember how to do this, and then can spend the time refreshing yourself. Okay, I just don't want this to be something that we did once in this class and that you forget about, because it turns out to be a very, very powerful and useful tool in the situations where it applies. Yeah. All right. Any other specific requests? Okay. Okay. Let's integrate this. We have the double integral of d, or double integral over d of yda. So it lies above the hyperbola xy equals 1. And the line y equals x, and below the line y equals 2. Okay, so not explicitly changing, but we're going to be setting up a problem and then analyzing how the different setups would be based on our first setup here. Okay, so let's draw this region here. Okay. All right, by the way, I want to say that this problem is harder than one that would show up on the test. I just picked a problem out of the review that was interesting and available. Okay, so we're told doing a good job drawing that line. The line y equals 2 is one of our boundaries, so I'm putting that in here. Okay, and we're also told that the line y equals x is one of our boundaries. Okay, and we also want to do xy equals 1. Okay, so we have this as our hyperbola here. Okay, and so we can rearrange this to make it a function of x. The graph for this looks something like this. Okay. And so the area for our integral is above this line, below this line, and above this line here. Okay. So what that means is that we are trying to integrate here. Make sense? Pretty easy to figure out that this intersection happens at 1, 1. It's the intersection between y equals x and xy equals 1. And so this is a problem that could theoretically be set up both ways. We could make it a type 1 integral by splitting the region up into 2 sections and integrating from whatever this value is to a 1, and then integrating again from 1 to 2, right? However, it's much easier to integrate it in the sense of a type 2 integral where we're going between functions of x. Okay? So our y values are going to go from 1 to 2 here. And what we need to do is make sure that we have our other boundaries in terms of functions of y. Our lower boundary is the boundary given to us by the hyperbola. So it's going to be 1 over y. And our upper boundary is just going to be y. And lastly, we need to make sure that our dx dy is in the correct order. Okay. Questions about this? Seems fine. Now we integrate. Okay. I don't know if anybody was spooked by the hyperbola that shows up in the integrand, but turns out that this problem is really easy after you get it set up. Check me, but I get 4/3. Okay. All right. So on the exam, what I consider to have been the domain of the Chapter 15 test is to give you maybe a more complicated version of changing integration order that involves a 3-dimensional surface or some potential change to spherical coordinates or something like that. Okay, that's not a final exam question. Okay, something like this that's much more manageable is what would show up okay? I may ask you, like I did on the chapter 15 test, if I'm remembering that test correctly, to maybe do one both ways. Okay, obviously this one doesn't lend itself to being done both ways, but that would be another variation on this type of problem. Is I give you the information enough to sketch the picture, and then you tell me the two different ways to set up and solve the integral. The computations will be on the shorter side since there's already time investiture in setting it up. Okay, if I'm asking you one where I'm just testing, can you integrate this double integral or triple integral? I'm going to give it to you, and the only thing to figure out is, should this be in spherical or cylindrical coordinates instead, or a triple integral or whatever, and then straightforward do the computation. Well, so where do we hide the question? Okay, so if we have a problem that looks like this, I'm not about to get a severe weather alert, am I? Okay, I thought I heard somebody's phone go off. All right, okay, so we have this expression here, and we need to figure out what this domain looks like. The place to start is with the hard limits we're given, since we happen to be given the range from 0 to 1 here. We're told that the y range goes from 0 to y equals 1. And in the x range, we are told that this is a bound. Okay. And then the last part here is, from this expression, we may infer that this is the equation x equals 3y. It can be rearranged. Will look like this. Okay. So if we were going to reverse the order of integration, we need to know which side of the expression we're integrating. Since we're going from this part here to this part here, this is the region for us. Okay. And so as written, the integration order goes this way. We want to change that. Sorry, I shaded in the wrong part of the image. I apologize. All right. As written, it's a type 2, so we're integrating here from 3y to x equals 3. And so what we want to do is we want to change the integration order to look like this. And so what that looks like is the integral from 0 to 3, the integral from 0 to 1/3 x, like so. Okay. So this one was fairly simple. Sorry. The reason I did the other example prior to this one is that I want to pick one that was too easy. This is kind of on that level to where it's really easy to figure out what the inverse equation was. And in this one, even though it didn't ultimately lend itself to being set up both ways, we do have some more interesting relationships between how the equations are constructed, right? Okay. Other topics. Yeah. Okay. So changing coordinates. We have a region here. The integrand is the square root of x squared plus y squared plus z squared. We're integrating over a volume. For the region lies above the cone, z equals x squared plus the square root of x squared plus y squared. And between these two spheres. Okay. So we want to get all this set up here. All right. So first question, of course, is what type of problem is this? What coordinate system do you expect us to use here? So we're definitely going to be setting things up in spherical coordinates. Okay. Organized here. Okay. So this expression here is one that you need to be familiar with in terms of, or at least if you're working homework problems, familiar with what this looks like. Okay, this is a cone, z equals the square root of x squared plus y squared. And it turns out that the polar angle here, pi over 4. Okay, this is something that's covered in the example for this section. All right, this is not one that I would likely give on an exam because you spend a lot of time figuring that out. You'd have to substitute in the way to solve this if you happen to have forgotten, need to know what the answer is. is you would plug in x and y in spherical coordinates. This equation would resolve to the point to where you would see that cosine of phi has to equal sine of phi. And so that tells you that phi has to be pi over 4. Because you need the trig function on both sides to be 1 over the square root of 2. Right? So if you forget, that's how you would solve it. But that's harder than, and just it's just one of those details that takes more time than what I would give you on the exam, right? I'd probably give you something that lined up with a coordinate plane. But we're going to need that limit for this particular example. Okay. And then otherwise, we have the cone, and then we have a sphere of radius 1 and the sphere of radius 2 that this cone cuts into, right? So the I can't draw this picture, all right, but that's the idea. Okay, we know the things that we need to figure out are the radius, and we need to figure out what the polar angle is, the range and the polar angle. We're going all the way around in terms of the azimuth, so we have the limits now. Okay. Azimuth is all of it. We're going all the way around the circle. We just discussed how to handle the polar angle part. And the radius is also easy because it's the region in between those two spheres. Does this make sense? Okay. All right, from here, it's a matter of making the switch to polar coordinates by plugging in the appropriate formula according to the standard parameterization. This is something that you either have memorized or put in your notes, probably both. And so we replace this with the appropriate quantity, but x squared plus y squared plus z squared is just r squared. We don't have to think about that part very hard, right? It could be the case that we plug it in and have to do some simplification if it were just x squared and y squared or something. But if you see that it's actually x squared, y squared, z squared, that's one of the equations for polar coordinates is x squared plus y squared plus z squared equals r squared. On the exam, you may have a case where, like we did on the recent exam, I'm pretty sure that this happened in one of the questions on the chapter 16 exam, where I gave you something like x squared plus y squared. And after you plugged it in, you had to do a little bit of simplification, usually using the Pythagorean identity in order to make sine squared plus cosine squared equal 1 after you do some factoring. Okay, so expect that sort of thing as a possibility. Sorry, I'm mixing my R's and my rows. Yeah, I don't want to confuse people. Rho squared. Okay, so we don't forget the Jacobian for spherical coordinates. Plug all that in there. All right, and now we're very happy with the way that this all worked out because we have this part here, which simplifies to rho cubed. And our integrand is separable because it can be written as the product of functions that depend on one variable each. And so we get the integral from 0 to 2 pi of d theta times the integral from 0 to pi over 4 of sine phi d phi times the integral from 1 to 2 of rho cubed d rho. All right, none of these integrals are difficult. You can work them out from here. Sense? Okay. Thing to keep in mind that might possibly come up in the exam would be making sure that you can handle reasonable versions of trigonometric functions to powers. Okay. This is an integral I expect you to be able to do, sine cubed. Okay. You need to know that you can replace 2 powers of sine with 1 minus cosine squared. Now it's a u substitution problem. Okay. You need to know how to integrate cosine squared by using the double angle formula. I switched, I don't know why I changed the Greek letter. Writing too fast. Okay. Now, obviously, there are higher powers of trig functions that can show up. Okay. I'm not going to make you go through the extra work of, say, integrating this. Okay. It's not any harder than the problems that I just listed. You just have more things to do because you use a similar identity to this one, multiply it out, and then apply the identity additional time if you have more cosine squareds that will pop up. So this should be something that you're remembering from Calc 2, how these things go together, right? There are basically 2 cases. There was use the Pythagorean identity and it becomes a u substitution problem, or apply this, which sometimes is referred to as the reduction of order formula, as you get higher and higher powers of your trig functions. You need to know trigonometric substitution. I'm not going to necessarily pick on you about that for the exam. Okay, that would be. I haven't mentioned it, so it's not likely to show up on the exam. There are other classes that you will, or at least should take in the near future that will, where that will come up. So I'll let them test you over that. Okay, how are we feeling? All right. So I recorded a couple of review sessions for my online class. Some of the questions that we covered might have been things that we covered in here from other review sessions or other things like that. They didn't take chapter tests, so I went through a little bit more slowly on a couple of things that we've already covered in here. You all want me to post those videos for that? Okay, because like one of the videos is almost an hour and a half long and the other one's about an hour long. Like it's a little bit on the longer side, but I can post those if that would be helpful. Okay. The other thing, and I'm actually very serious about this, it is not required, but I would very much like to have the opportunity to speak with each of you for a few minutes prior to the final exam, so that if I need to give you back tests, because I don't carry the tests because they're heavy. All right, I already carry like almost 30 pounds worth of electronics with me. All right, paper, and it turns out paper is heavy, so that's why I don't have the exams with me all the time. So if you want to grab an exam that you happen to have missed in the past, or ask questions about an old exam because you looked at it studying and realized that I did something stupid or something that doesn't make sense when I graded it, we can sort that out quickly prior to the final exam, and then also touch base about um, some of the more granular properties of course grade assignment. Um, when I do grading for the semester, I don't just look at exactly the formula in Blackboard. Okay, that's one of the ways that I try to evaluate you. But I can't discuss anything more specific about it unless I meet you on a one-on-one basis due to confidentiality stuff and all that. So I would like to meet with you. If I don't see you between now and Tuesday, then I will see you on Tuesday. Good luck, and I will keep an eye on my email to make sure that I can answer questions not about grades, because I can't for confidentiality reasons, but about the final exam, so that you can get as prepared as you can. All right. Also, so enjoy the rest of your week. Good luck on your other finals as well, and I will see you when I see it.